Hello, I'm Diego from Revision Dojo and welcome to this new video series on the IB Physics 2025 syllabus. Today we're going to be looking at A.1.1 describing motion. It is essentially a toolbox of different physics concepts and tools that we can use to describe and analyze motion in different dimensions. Today we're going to look at vectors and scalars, speed and velocity, graphing motion, instantaneous and average speed, and SUVAT equations. Let's get started. Firstly, let's take a look at the learning objectives of A.1.1. I highly recommend you write these down, and as we go through the lesson, you highlight the concepts that you need a little bit more work with, and you tick those that you are confident in understanding. These are the formulas for A.1.1. As you can see, they make up the entirety of the section of the formula booklet on A.1 kinematics. These four formulas are the SUVAT equations that we will be seeing at the end of this lesson. So, the first section of this subunit is vectors and scalars. What we need to understand at first is that when we talk about vectors and scalars, we are talking about quantities. We are talking about types of quantities, actually. The definition of scalar is a physical quantity with size, but no direction. The definition of a vector is a physical quantity with size and direction. These definitions were directly taken from the textbook, and I highly recommend you memorize them. In physics, there is not that much memorizing, but there are still some key definitions and terms that you need to remember. Here, something we might want to define is the concept of physical quantity. What is a physical quantity? Well, a physical quantity is actually just any number you get in physics. A quantity is just a number, and physical, well, in the physical world. In the case of physics, it's something that represents a variable in a question. It can be, for example, 15 newtons, or 200 meters, or also 5 joules. All of these are physical quantities. A scalar, as you can see, has size but no direction. And here, I would like to point out that there is another term for size that is actually magnitude. If you do math HL, you might have encountered vectors before, and you might know size as magnitude. They are essentially the same thing, they are both completely correct, but personally, I prefer magnitude as it is a little bit more mathematically correct. So, a scalar has no direction. What does that exactly mean? Direction is a concept that is a little bit tricky to understand. But with an example, it should be relatively straightforward. Let's assume you have an object here, a box, and you decide to apply a force on said box. That force is going to have a magnitude. It can be, for example, as we said here, 15 newtons. Then that box is going to move. In what direction is it going to move? Well, in the direction of the force applied. And this is the important thing here. If you applied this force, let's suppose in a different direction, so for example here, it might still be 15 newtons, but that force would make that box move in a different direction. As you can see, force is a vector quantity because it has a direction. It is applied in a certain direction. You can name that direction, for example, by saying it's going north, it's going at a 45-degree angle, it's going left or right. There's many ways of defining the direction of a vector. But in any ways, a vector quantity always has a direction. The opposite is obviously the scalar, which has absolutely no direction. Here, take a look at the quantities we wrote down here. Which ones do you think are vectors and which ones are scalars? Of course, you already have an answer. Right here, 15 newtons is a force, because newtons is the unit of force. Therefore, it must be a vector. What about the other two ones? 5 joules is an energy, or it can also be work. 200 meters is a distance or displacement. We will see the difference between distance and displacement in the next section of this lesson. However, for now, take these quantities and tell me, which ones do you think are vectors? If you answered displacement, that's right. Energy and work are both directionless. For example, you can say that a certain object has a certain amount of kinetic energy, but there is no direction given to that energy. Same with work. You can say an object is doing work, however, you don't have to specify in which direction it is doing the work. Work does not have a direction. Distance is similar. Distance, we'll see a little bit later, is a measure of the length of a path taken. Therefore, because it's a measure of length, it has no direction. Displacement, on the other hand, it's a measure of a difference in position. Again, don't worry, we'll be seeing this in the next section. But because it's a difference in position, you need to state in which direction that difference is. For example, if you are at point A here, and you move to point B, your displacement was downwards. If you were at point C, well, if you're going to point C, your displacement is not quite downwards, it's more at an angle. All right, as promised, now let's see the difference between distance and displacement. They are a perfect example of a scalar and a vector quantity. As I stated before, distance is a scalar, while displacement is a vector. Despite the fact that they're both measured in meters. Again, as stated before, distance is a measure of the path taken. This is very important. It's just a measure of the path taken. For example, if you're at point A and you're going to point B, but you don't take quite a straight line, here, your distance is going to be relatively big. It is going to be much bigger than just a straight line from A to B. So keep this in mind, keep this little definition here. Distance is the measure of the length of the path you take. On the other hand, displacement, as we stated before, is a difference. Displacement is a difference in position. As you can see, I used delta here. In physics, we use delta to state a difference or a change in something. This is a very important notation that I recommend you keep in mind. So, displacement is a difference or a change in position. So, taking the same example, you have point A and point B, your displacement is going to be the difference between your position at A and your position at B. So it's going to be a straight line between the 2 points. It does not matter what path you take, it doesn't matter the distance you cover. Displacement is always in a straight line as it just takes your initial and final position and works out the difference. This is a great example of a scalar and a vector that use the same unit and represent similar things. Now, let's do a quick exercise. So, here are 2 tables. I invite you to copy them down and write down all the vector quantities you can think of and all the scalar quantities you can think of. The important part here is, remember, vectors have a direction. I already told you a couple of them. So for vectors, we have forces, and we also have displacement. I'm not going to write it all down. Then scalars, we have distance, of course. And we did mention energy before. And work. So, try to think of different quantities. I can give you a few examples like speed and velocity. They both represent very similar things, but which one is a vector or a scalar? Try to think about that and you'll be ahead of the next part of the lesson. Other quantities can be things like temperature, or mass, or charge, or current. Any other quantities like that, try to think of them and write them down in your vectors and scalars column. Then check your answers with your classmates or your physics teacher or tutor. This is a very useful exercise because you do not want to be going into a physics paper and be wondering if a certain quantity is a vector or a scalar. Do you have to take direction into account? How does it work? You do not want to do that. So you want to really know your vectors and scalars pretty well. Trust me, it can save you quite a few marks. All right. Let's take a look at the second section of this 8.1.1 describing motion subunit. It is speed and velocity. So, speed and velocity are the scalar and vector quantities that use the meters per second unit. So, meters per second, more commonly written in physics as meters per second. These notations are equivalent mathematically, just like. However, the preferred one is the one in the middle right here, meters per second with the negative power. Keep that in mind for the future. So, if I were to tell you speed and velocity, try to think about it. Which one do you think is a scalar and which one do you think is a vector? Depending on your previous physics knowledge, you might have absolutely no clue, or you might already know that speed is the scalar and velocity is the vector. But let's take a look at why that matters and what we use it for. So, the important thing to keep in mind here is how they are calculated. So, for example, speed is distance over time. The important part again here is distance. So speed is distance over time and velocity is displacement over time. Of course, you should be able to tell already that velocity is a vector quantity because it comes from displacement, another vector quantity. And this is a concept in physics and ultimately also in math that's quite important to understand. If to calculate a certain quantity you need a vector, then that final quantity is going to also be a vector because it has a direction. It keeps the direction. A quick way to understand really why this matters is to see that speed, for example, cannot technically speaking be negative. Let's take a look at a quick example. So, let's assume you consider this direction the positive direction in terms of velocity. So that means that anything moving in the direction of that arrow is moving with a positive velocity. Essentially, it's the forward direction. Now, if you have a car moving in that direction, for example, then it has a positive velocity. If its velocity there is 10 meters per second in that direction, then its speed is also equal to 10 meters per second. However, let's suppose a car suddenly decides to stop. And it starts moving backwards. Then, what do you think its velocity will be? Well, as I stated before, the positive direction is the opposite to the direction it's currently going in. So it must be minus 10 meters per second. Indeed, that would be right. However, what is its speed if its speed has no direction? That's right. Just 10 meters per second, just like it was before. So this is a quick way to understand the difference between velocity and speed. Just speed is a general measure of how fast it's going, whereas velocity actually gives you a little bit more information. And we'll see that that matters much more a little bit down the line. So let's take a look at our first sample question. A plane flies over Singapore at 7:20 and over Hong Kong at 12:10. Given distance between the two cities is 2,572 kilometers, and assuming the plane is moving at constant speed, calculate said speed. So here let's highlight the important things. We have here some times, we have a distance as stated here, and also constant speed. And we are being asked to calculate the speed. Perfect. You should always do this with all of your questions in physics. Again, I'm really not joking unless you're already much further down the line in your revision, you're very confident with many of the questions and you can just rush through them. If you don't have the confidence, do this. Highlight every quantity, every detail, every assumption in particular, because the IB will try to trap you and you need to be ready to see those traps. Let's see, it's asking to calculate speed. Let's recall the formula for speed. So, distance over time. So, looking at this formula, then we know that we need two different variables. So we need distance and we need time. We have our distance, it's right here. And we do have time. We have a starting and an end time. So now what we need to work out is the difference in time between those two moments. So quite simply here, if we do the difference between 10 hours 10 and 7 hours 20, then we know that that is 4 hours 50. However, we know that we want a speed, so we want that answer in meters per second. We need meters and we need seconds. Let's start by converting these. So 4 hours 50, let's start by doing 4 hours times 60. So that's for the minutes that we're going to be working out. That is 240 minutes, which of course then we can add 240 plus the 50 minutes. That gives us 290 minutes, which we convert in seconds by multiplying by 60. And it gives us 17,400 seconds. So we have our seconds, now we need our meters. We have a figure in kilometers. We need to convert that. So 2,572 times 1,000. That gives us the very big number of 2,572,000 meters. All right, we have our two figures here. To be clear, this is a... Now that we have these two, we just have to grab our little formula up here and do our calculations. Let me make some space for that. So our speed is going to be 147.816 meters per second. If you have any questions about this first sample question, just drop a quick message in the comments. We'll make sure to answer it. All right, now let's see the second sample question. Ben starts running from point A at 8 meters per second. Let's quickly highlight 8 meters per second from point A. Amy leaves 2 seconds later and starts running perpendicularly to Ben at 5 meters per second. 10 seconds after Ben started running, what is the shortest distance between the two runners? And again, we assume constant velocity. Okay, so this question here sounds confusing. It's definitely quite convoluted and has lots of information. Also, it's important to highlight this and correct the mistake. There's an N here. All right. Anyway, the best way to approach this question is to draw a diagram at first. So we have point A here, and Ben starts running from point A. So let's assume Ben starts running in this direction at 8 meters per second. Then 2 seconds later, Amy is going to leave perpendicularly. This is an important term. It's a math term, but that is used very, very often in physics. So perpendicularly means at 90 degrees. So let's say that Amy runs in this direction. We have a 90-degree angle here. Perfect. And she runs at 5 meters per second. Okay, so we have our two runners here. We want the shortest distance between the two runners after a certain time. So we know that they both move in these two lines and there's 90 degrees between them. So how do we find the distance, the shortest distance between 2 points on lines like this? It's a bit of a math question, but again, physics is quintessentially math. So you need to have your math knowledge in your head at the same time as your physics knowledge. I know it's not easy, but you'll get better at it, you'll see. So how do we calculate the shortest distance? By making a triangle. Indeed, the shortest distance between 2 points like this is always going to be a straight line between the 2 points. How do we find that? Well, through Pythagoras. Indeed, the shortest distance between 2 points on lines like this, on perpendicular lines, is always going to be a straight line between those points. And how do we find the length of that straight line? Well, as you can see, this looks a lot like a right angle triangle. So we use Pythagoras. Pythagoras, I remind you, is this. And therefore, we need A and B. The length of A, let's assume A is how far Ben ran, so here, is going to be the distance that Ben has covered, or the displacement of Ben. Here it doesn't really matter because Ben is running in a straight line. Then, for Amy, it's going to be exactly the same thing. It's going to be her distance or her displacement. How do we find that? Well, let's recall our speed formula. Or velocity, again. Here it doesn't matter because we're talking about straight lines. We remember that this formula is distance over time. This time we have speed. Here, 8 meters per second, 5 meters per second. And we have time, so we just need to do some equation rearranging. So here, I'm going to show you the shorthand way of writing the equation, which is v for velocity equals displacement over time, like this. Most of the time we're going to be using velocity and displacement, so that's what I'm going to use here. But again, because it's a straight line, it doesn't really matter. So, using this equation and rearranging, to solve for displacement, we have v times t equals s. Alright, well, that's it. We need to do the math now. Little warning sign though. Here, this is an S for displacement. The reason why it's an S is actually because it comes from the Latin word for displacement, which I'm not going to state here, but all you need to know is that S is displacement, not time. It does not mean seconds. T is time, T is going to be seconds, S is going to be meters, it's displacement. Very important thing to remember. You can easily get confused in the test, and that really will cost you marks. Now, using this formula, we just have to find the displacement. So how do we find it? Velocity here, 8 times 10, because 10 seconds after Ben started running, well, Ben has been running for 10 seconds, which gives us 80 meters. For Amy, there's a little bit of an extra step because Amy, of course, leaves 2 seconds later. That means she has been running for 10 minus 2 seconds, which of course equals 8, so then we do 8 times 5, and that gives us 40 meters. So now we have our A and we have our B. We simply use Pythagoras. I'm going to make some space for that. We remember our A equals 80 and our B equals 40. So, well, 40 meters and 80 meters. Units are important. Within your calculations, forgetting the units is not a problem at all. However, for your final answer, it's very important. So I recommend keeping the units throughout your work. So, 80 squared plus 40 squared, square rooted. So here is our answer, 89.44. Again, we want 3 significant figures, so 89.4. Did you spot it? Indeed, the units. Do not forget the units. It's very important. Let's just quickly recall the quantities of motion that we looked at. There's distance and displacement, both measured in meters, and there's speed and velocity, both measured in meters per second. Okay, so as you know, and we've already talked about this, distance and displacement allow you to calculate speed and velocity. The only thing you need apart from that is, of course, time. So let's keep these in mind. What is graphic motion? What do we mean by graphic motion? What we mean by that is illustrating a certain movement, so an object moving in a graphical manner. And there are 2 graphs that we're going to look at. All right, let's take a look at a distance-time graph. So a distance-time graph is a graph with distance on the y-axis and time on the x-axis. It's very important that you do the axes like that. That's why it's called a distance-time graph or a distance-over-time graph. The first word in the name of a graph is always going to be the y-axis variable, at least most of the time. So what we are going to learn today is how do we build a distance-time graph from a situation? What does that tell us? How do we analyze it? And what exactly does it represent? That's why I've designed this little situation here where Timmy has to go to school. And for that, he has different sections in his trip to school. He has 3 sections. First off, he walks for 2 minutes, and the distance he covers there is 100 meters. Then he takes a bus that takes 5 minutes. and that covers a distance of 400 meters. And finally, he walks once again for 5 minutes, and he covers a distance of 100 meters. Already you can see that Timmy is going much faster in the first leg of his trip than when he is getting close to school. We can assume that this might be because he doesn't want to go to school, so he walks much slower, or maybe he's afraid to miss the bus, and so he runs for the first 2 minutes. Anyway, that's not very important. But the important part here is to understand the situation so we can graph it. Let's start by representing this movement that Timmy has at the very beginning. So, he covers 100 meters in 2 minutes, which is 120 seconds. As you can see, the graph is in seconds and meters, so it's important we stick to those units. Always use SI units in your graph. Seconds, meters, kilograms. Always use SI units. If you don't know what SI units are, it's a very important thing to revise. I recommend you quickly look it up because it is a very simple part of physics. Alright, let's actually dive into drawing the graph. As we can see, 2 minutes being approximately 120 seconds means that this leg of the trip must end around maybe here. Alright, well, we can already draw the first line of this graph then, here in the middle. It goes from 0, of course, time 0 and distance 0, it's Timmy's house, up to that point. Now, the next leg lasts 5 minutes, which is 300 seconds, and it covers 400 meters. So 400 meters, we know that added to 100 is 500, so this leg of the trip must end around here. And then we also know that 5 minutes being 300 seconds means it must end around here. 300 plus 120 seconds from before, that gives us approximately 400 and something. So 420 exact. Then we draw a point. There we go. Alright. And then, alright, well, now for the final leg of the trip, we know that it takes 5 minutes, so another 300 seconds, which brings us to a grand total of 720 seconds. So approximately here, and then another 100 meters, which brings us to exactly 400 meters. Perfect, we can draw our last line of the graph. And then I'm just going to make sure we see very clearly where each leg starts and finishes. Perfect. Alright, so this is our distance time graph. Now, what information can we gather here? Well, I would like to point out that the equation of speed or velocity, they are basically identical, so I'm going to use the same, is this one. We have at the top here displacement or distance, and at the bottom time. Do you see it? Do we see speed somewhere on this graph, or can we extract it from this graph? The answer is yes. It's a gradient. Because the gradient is always calculated by rise over run. So for example, the gradient at this point is going to be 200 over, well, approximately 250, maybe, something like that. And that is also actually the gradient of this entire section because it is a straight. Then we can also calculate the gradient here if we want to figure out how fast Timmy was running to get to the bus, and the gradient here to calculate how fast Timmy was walking from the bus stop to the school. So this is one of the most important pieces of information for a distance time graph. You must also know how to build one based on a situation, just like we did right here. For a distance time graph that is mostly everything, you just need to make sure to always respect the rules of making a graph. So always check the situation beforehand so you can decide your intervals here. You can see that mine were pretty good, but not exactly. For example, the 600 here was unnecessary. It should have been maybe something like 500. And also here, these two at the bottom were unnecessary as the graph did not go nearly that far. So do not do that and actually read the situation. Make your axes, the scale of your axes in respect to the situation at hand. Alright, let's move on. Alright, let's take a look at velocity time graphs now. We're going to switch it up a bit, and this time we're going to work from the graph and deduce the situation from it. The questions could ask you either of those things for either of the graph types. Alright, so first off, let's take a look at this graph and at the different sections it has. We see that there is a negative gradient section here. Here, because it's a velocity time graph, let's see what we can deduce from it. The car here must be losing velocity because we have a negative gradient. That doesn't mean it stopped, and that doesn't mean it's going backward. This just means that it is slowing down, and that's the important part. So the car is still going in the positive direction because we have a positive velocity, it's above the x-axis, but it's slowing down. Then here it crosses the x-axis. That means that the velocity turns negative. At this point, right here, velocity is equal to 0. That means the car has stopped. So, for example, something here that we can deduce is at t equals 20, car stops. So this is a piece of information we can deduce. Then the velocity becomes negative. That means that the car starts going backwards after t equals 20. Right here, we see a negative gradient, once again, but because we're below the x-axis, that means that the car is actually speeding up, just in the negative direction. The velocity is getting more and more negative. Its magnitude is increasing, but its direction is negative. Remember the vectors and scalars bit at the beginning of the lesson? Well, now that comes in handy. Here there's a flat area in the graph that means constant velocity, so that means the car is not changing velocity in any way, it is maintaining, in this case, negative 3 meters per second velocity. And then the car starts, once again, slowing down. It's still moving backwards in this region right here. It's still moving backwards, but it's slowing down. We have a positive gradient, but with a negative value, which means the magnitude is decreasing. Then for this bit here, it is quite normal. It's increasing, means velocity is increasing, the car is accelerating forwards. Oh, that's a new word, acceleration. Most of you should have heard this before if you've taken physics, but let's just assume we need to review it. The concept of acceleration is the change in velocity, and that is very, very important to keep in mind. The equation of acceleration, which is not given in your data booklet, is the change of velocity over the change in time. So acceleration is what we call the rate of change of velocity, how much velocity changes per unit time. So in the previous distance over time graph, we saw that the gradient meant velocity. Well, similarly, here in the velocity time graph, the gradient means acceleration, and you should be able to understand kind of why. Because velocity over time happens to be, well, exactly the formula for acceleration. So you can find the gradient and then deduce the acceleration at any point on this graph. For example, here we will have a negative acceleration, just like we will here. Acceleration is also a quantity that has a direction because it is based on velocity that has a direction. All right, so acceleration was a very important part that we had to quickly look at. Hopefully you'll understand that. Again, as soon as you get some questions done, it will be much clearer. Then the second piece of information that we can actually extract from this graph is displacement, and this one is much trickier. So if you remember earlier in the lesson, we used this formula. It is simply the velocity formula rearranged. Here we see that displacement is actually the product, so multiplication, of velocity and time, which happen to actually be here. We have both values, which means we should be able to deduce displacement. But how do we do it? Well, let me answer that question for you. You find the area below the graph. Because how do we find the area of something, for example a square? It's exactly the same thing on this graph. You multiply the x-axis by the y-axis, and then you find the area below the graph. This is a concept that is quite difficult to understand if you do not have calculus knowledge. But once you learn about calculus, this will be a breeze to understand. For now, all you need to know is that to find displacement, you need to find the area below your velocity time graph. So this area down here, for example, is the displacement of the car between t equals 40 and t equals 80. Here, this is quite a relatively easy graph. To find the area there between t equals 40 and t equals 80, we just have to find the area of a triangle. So here we have 20 at the bottom. Here on the side we have 10, so we know that it's 20 times 10, and because it's a triangle, we have divided by 2, which actually is really straightforward. It just gives us actually, my bad, this is not 20, this is 40, and it's 200. Perfect. So that's just how you find the area under the graph and the displacement. For slightly more complex shapes like this right here, you first have to divide the graph into more easily calculable areas. For example, here we have a rectangle and then two triangles, which are much easier to calculate than this weird trapezoid type of shape. Alright, that will actually be it for a velocity time graph. Now, you might ask the question, but what if the graph isn't straight? What if it's not easy to calculate? For example, what if the graph looks like this? Well, that is actually a little bit harder to do, and again, without calculus knowledge, it's quite tricky, but don't worry, I'll explain it. We'll actually talk about the slightly curved graphs in the next section of the class, but here I can already show you how to calculate, or more approximate, the displacement in a velocity time graph that is curved. Here what you do is you want to find the area below the curve. So you divide the curve into small rectangles that approximate the shape of the curve. Etc., etc., etc. Then you just find the area of all of those rectangles and you add it together. And that's how you find an approximation of the displacement with a curved graph. These kinds of questions are always quite lenient in terms of the margin of error, so even if your rectangles aren't perfect, you should be getting an answer within the range of accepted answers if you do this technique. Again, I highly recommend you go practice on questions, and if you still have some doubts, just drop a comment. Let's move on to instantaneous and average speed. So, as you can see, there's a little example graph here. Most of the time, you're not going to have graphs with straight lines. That is an ideal graph. It might happen a couple times in certain of your questions, but most of the time you'll have curved graphs, just like in real life. You don't always keep a constant speed, and that's the most important thing. Most of the time, you do not always go at exactly the same speed or velocity. So that's why graphs, distance times graph specifically, tend to look curved. So that's why there are two terms that you need to know. First off, instantaneous speed. So instantaneous speed just means speed at a point. Remember that, it's speed at a given point. So for example, the instantaneous speed at this point is going to be the gradient of the graph at that point. How do we find that? We'll find out in a bit. Average speed, as the name indicates, is the average speed in a certain interval of time. So for example, I can try to calculate the average speed between t equals 30 and t equals 40. Now, how do we find those? Well, first off, instantaneous speed is a little bit tricky because you have to find the gradient at that point. How do you find it? With a tangent, if you have not heard of those. Those are a line that exactly just touches the graph. That line must pass through that point and that point only, and it just touches the graph and goes along. You are meant to draw these with a ruler. For example, this is not a very good tangent. This is more like the tangent of maybe this point. Then, once you've drawn that tangent, you have to find that gradient, the gradient of that given tangent. For example, here we do rise over run, so the rise here we can estimate to be approximately 25, and then the run approximately 18. We find that gradient, so rise over run, which is approximately 1.38, and it repeats. So the instantaneous speed at that point is approximately 1.39 meters per second. So that's the speed at that point. Average speed is quite a lot simpler. You simply have to draw a straight line between the 2 points, so the beginning and the end of your interval, and then calculate the gradient of that given line. And there you get an average speed. So in this case, we have very approximately a gradient of 4/10 approximately. So that's the average speed 4/10 meters per second. I hope that is relatively clear. I know we're going through this quite fast, but there is a lot of content in this unit, and instantaneous and average speed are both concepts that should be pretty straightforward to understand once you start doing questions with them. Let's move on. Congrats if you've made it this far in a single watch. I would expect most of you to have taken some breaks in between, but I promise this is the last section of this lesson. 8.1.1 is the most important section of 8.1. The other two sections that we're going to be seeing in the next videos are much, much lighter, don't worry. So let's take a look at SUVAT equations. They are also known as the kinematic equations. If you're wondering why they are called SUVAT, well, it's because those are all the variables that go into these equations. Let's take a look at them. So first we have S. If you remember well, S is distance or displacement, but here I'm going to be talking about distance. Then U is initial velocity or speed. V is final speed or velocity again. A is acceleration. And finally, T is of course time. Alright, these are very important to remember. It's very easy to confuse, especially U and V, so remember these. Now, I need to state a basic assumption of SUVAT equations. You can only use them with constant acceleration. That means you can only use it where the speed time graph or velocity time graph of the motion you're looking at is a straight line with constant gradient, just like the one here right below the formula. If there's different gradients, but they're all straight, you can always break the motion down into different sections, like we did before when we looked at speed time graphs. Let's see how we can find these little variables on our speed time graph. It's relatively easy for example, initial and final speed. Initial speed is of course where the graph begins, right here. Initial speed can also be 0, it can be all the way at the bottom here. Then final speed is obviously where the graph ends. So we have a U, and then V is going to be here. Then acceleration, if you remember well, is the gradient of the graph. So it's going to be measured using rise over run. Time is of course just the interval of your graph. So time is here at the bottom, T. And finally, distance, if you remember well, is the area under the graph. And then what we need to do is divide this graph into a triangle and a rectangle and find the areas. Alright, let's see how we do that exactly. So, to find the gradient, we need to do rise over run. Here, rise is equal to V minus U. I hope you see where that comes from. Then overrun is obviously T. So V minus U over T equals acceleration, because it's rise over run. Then, for the area, we divide, of course, this in a rectangle and a triangle. So distance is equal to the area of this triangle here, which is 1/2 times V minus U, again we are using the same rise, quote unquote, times T. So that's the base, and the height is V minus U. And then plus the rectangle, which is just U times T. Alright, so that's how we find all of these variables on this graph. We have the gradient, which is acceleration, we have distance, the area under the graph, and final and initial speeds, as well as time. Now we're going to take a look at how we derive the kinematic equations. We can finally look at them, they're right there in the middle. Be careful, the formula booklet actually writes them in the wrong order. The fourth one is at the top, and then there's a first, second, and third. That's how they're labeled, for example, in textbooks. So we're going to look at them in order, not in formula booklet order. Without further ado, let's start with the first equation of motion. So the first equation of motion is just V equals U plus AT. And it's a very, very simple derivation, as we simply take the gradient that we got before, so our rise over run, and we rearrange this. That's it. That's the first equation. The first equation of motion is the equation that does not need distance. It just needs initial and final velocity, acceleration, and time. So if you have a question where you're looking for one of these variables, but you're lacking distance, then you use this equation. Perfect. That's it for the first equation of motion. The second equation of motion is the equation for distance. So here, it's quite obvious what we're going to do. We're going to look at the area under the graph that we had before. But as you can see, we have acceleration in this equation. So how do we find that? Well, using once again our gradient equation here. And now we can substitute this back into here. We've derived the second equation. The first and second equations are those I call the fundamental equations of motion, because those are made straight from the information we get from the graph. So let's look at the third equation of motion. All right, let's take a look at this third equation of motion. This one is the one that is lacking t, so it has no time. And to find that equation, what we need to do is use the first and second that we found just before. So as we stated before, this equation doesn't have time. As both equations have t, we can rearrange the first equation so that it equals t, and then substitute it into the second equation to get rid of time. So let's begin with this one, and rearranging this so that it equals t, and then we substitute it into this formula right here. And now this is just pure algebra. Trust me, if your algebra skills aren't on point, it'll be very hard to get above a 5 in physics. So work on them, practice your algebra skills, because they will win you lots of marks in the exam. Ideally, you should be doing this derivation with me, or pause the video, do it on your own, and then come back for the answers. Alright, so that is the derivation. If you have any questions about the math here, do drop a comment. I understand it can be a little bit complicated, and each step can demand quite a bit of algebra. So if you have any questions, please don't hesitate to ask. That is it for derivation of the third equation of motion, which as you can see is a child of the first two equations. Now for the fourth equation of motion, I am going to leave the task to you. Try to derive this equation. What I can tell you already is that the variable it lacks is acceleration. So you don't need acceleration, or rather, you might have to get rid of acceleration. We can, however, move on to our final sample question of this lesson. I know it's been a marathon, it's been difficult, but don't worry, we are there. So this is a fairly simple question with SUVAT equations. So a tennis ball is shot vertically upwards at time t0. The ball has a velocity of 0 at t equals 5 seconds. Air resistance is negligible. So here we need to look at our variables. We know that the ball is shot at t equals 0, and that at t equals 5 seconds, the velocity is 0. So we can say that our t is equal to 5, and our final velocity is equal to 0. Also, we assume in this kind of questions that this is going on planet Earth, so we know that the acceleration is going to be negative 9.81, because the ball is being slowed down by gravity as it is shot vertically upwards, and it is the only acceleration acting on it because air resistance is negligible. So we're looking for the initial speed. Let's look at our equations. Which one has all of these variables? The first one, first equation of motion. So v equals u plus at. We simply rearrange the equation to look for what we want. So v minus at equals u, and then we substitute the values. Perfect. So again, we always do answers to 3 significant figures, and the proper way of doing it is you put your answer here with as many digits as your calculator gives you, and if it gives you too many, just add 3 little dots like this. And then you use the approximation here, equal sign, and you put your actual answer to 3 significant figures. Easy SUVAT equation. Lots of them are like this, though. You might have to extract more information from a graph, or maybe do some extra calculations before you get to the SUVAT equation, but most of the equations will be like this. You will have certain variables, and you need to find which equation actually fits them all and doesn't need any more information. Alright, well that will be it for this lesson. Finally, we have reached the end of 1.1.1. You've got all the knowledge you need to build on this forward and continue practicing doing questions. If you have any additional questions, any doubts, please drop us a comment and we'll make sure to answer in prompt delays. Have a good rest of your day, have a good study session, and if by any chance you're studying for your exams, good luck, hold strong, you'll get through it.